All right, next I'm going to talk about OpenCL, which is a framework for using or computing between CPUs and GPUs. The idea here is that you have a CPU which ends up being a high number cruncher. And so we want to use the GPU capabilities or the type of processor it is in order to facilitate or aid certain types of computations. Now what's going to end up being is there's a lot of programs that can be sped up significantly by utilizing the GPU, although there are some drawbacks to using the GPU that will make it so that other type of compilation, or I should say other type of workloads, are not very fast or useful to send over to the GPU. So this was on the NCSS user forum, March 20th, 2012 by George, I'll just call him George. So top 3 in 2010, yeah, I know this was 10 years ago, but this has not changed too much. You have a lot of processors and a bunch of GPUs, or one of them just had a bunch of processors, another one had GPUs. If you actually look nowadays, most of the top 10, they all have tons of GPUs, and so a lot of people are trying to utilize the GPU in order to facilitate computation. Before 2009, I don't know how many of y'all remember that, but most GPUs, well, they weren't quite a novelty, but mainly used by gamers and hackers. There was a time where hackers were using these in order to crunch numbers and also for Bitcoin mining. But it turns out that nowadays for supercomputing it's very useful, and they're going to go through an example here. And they did an example of doing a simulation of molecules, and this can be useful for health research as well as physics research, a lot of different ones. But the idea is that for each point P and for each atom that's inside of these points, you do a computation in order to see what the interaction would be. We'll just say that there's a computation they need to complete for each of these atoms. And the reason for that, before I move on, is they're trying to simulate. And what happens a lot in simulations is you have a step to where you do all the computations based on the current state, and then you move, once you have those computations, you take that as your current state, and then you again go to the next step where you figure out what the next computation levels are going to be for all your atoms. And once you have all that done, you flip it back to the current state. And this is a very common way in order to do simulations. So what they're trying to show is that on a GPU, it takes, well, they say 0.00 seconds or very few seconds, while it may take up to a minute on an actual processor. And we're going to talk about how that's done. Now, if you get down to 16 threads on 16 cores, about 5 seconds. So there is actually a pretty significant improvement. And then OpenCL did 0.18 seconds. What did they talk about at the beginning? Oh, this is just to give you a picture of what the final result would be. And actually what they're doing is that these are all the atoms, and they want to see what these atoms affect our moving out. Looks like they're trying to find some sort, I don't think it's gravity, but I don't have unfortunately I don't have the exact information with me. So 16 threads. The reason for this, and then putting it all together, is about 5 seconds, but using just the GPL is 0.18 seconds, which is significantly faster than a single core. So if you look at the speed up, CPU, they ran some other timings for some other situations. So if you took the CPU as a baseline for 20.5 seconds, using GPU without optimizations, 0.15, speed up 136. Now this isn't a percentage, this is a factor speed up. So this is a crazy speed up. And then optimized GPU is even more. So in other words, for this application, the GPU ends up being a significant performance boost. Why are GPUs so fast? Well, if we were to compare the architecture of the two different, you can tell just by the picture that it looks different, but you can't really tell why. And I'll explain real quick. The CPU is used for doing serial type of operations where you're doing one instruction after another. And you might have 4 or 8 cores to do some type of parallel processing. The GPU, on the other hand, is not doing serial communication. It's doing something with the frame buffer in order to compute what the next image needs to be, usually inside your game. And so what it is, instead of having 4 cores, you might have thousands or tens of thousands, or even in some situations, hundreds of thousands of cores. But unfortunately, the GPU is very terrible at doing serial computations, and I think these slides will hopefully go into more details with that. So the bus on these old ones, 512, 128, 128 is the CPU. The memory bandwidth, look at that, 141 gigabytes versus 12, of course that's much higher. There's a big cache difference, and in the GPU, I had 240 cores in this situation, although nowadays you can have easily up to 1,000. So why should I care about heterogeneous computation? It can definitely increase computing power, as we just saw. It went from, 56 seconds to 0.18 in that situations. And this is called heterogeneous because these are different CPUs. You have your CPU, which is used for a type of serial processing, and then you have your GPU, which is done for your parallel processing. And then if you have a program that utilizes both, it's called heterogeneous computing because your programmer is actually using or utilizing both CPUs. So in other words, when you run your game, you are doing a heterogeneous computation. So what is OpenCL? OpenCL is a tool in order to move these computations over into the GPL. It's a standard parallel programming consisting of parallel processors like CPUs and GPUs. It was developed by many companies. Originally, NVIDIA came up with something called CUDA, but that was very specific for NVIDIA, so people eventually got together and came up with an open library called OpenCL. And most hardware vendors implement these OpenCL primitives so you can utilize it for their cards. What is a device? Well, it's some type of processing unit. You can actually run OpenCL on your processor if you wish, but most of the time you want to use it for your graphics card because using it on your processor in general is not going to have a performance boost. So normally inside of a supercomputing environment, what they have is some CPUs, and each CPU is hooked up to a GPU. What's nice, okay, so some features, clean API, it's ANSI compatible. That just means that they've made sure that it conforms to all the standards. It can utilize all the well, I shouldn't say that because you might be using something else, but it does allow you to leverage the GPU. It is IEEE compliant for rounding behavior. That's by the way, the floating point computation. And it does provide some guidelines for some future hardware improvements. This is a fine-grained computation, and what that means is that it's not talking about, well, let's go to the difference. The grid would be something like the World Wide Web, where it's very coarse-grained and you send some data out and it comes back. SIMD is very fine-grained, where you're using something that's very specific on the processor, and then you have everything in between. P-threads is you're still working on the processor, but you're utilizing the different cores. MPI is usually you're on a local area network connecting different computers together. And then the grid is you're on the World Wide Web communicating over the internet. So one way to think between coarse grain and fine grain is what's the distance between the workload. Over here it's almost nothing because it's all working on a single core. Here it's very low because it's still working on a single core utilizing multiple cores. It's working on a single processor, utilizing multiple cores. MPI is going into coarse grain because you're utilizing different machines, so it has to go off the actual computer onto another one, but usually it's within a local area network. And then grid is even more wide space because it might be going across the world. MPI is usually on a site like CSU, while grid, you might have CSU, and then you might have universities up in London or whatnot. OpenCL, the idea. So how does OpenCL actually improve performance? Basically remove one level of loops. So instead of doing for I is 0 up to n, you get the ID and then you just do the computation. How does it take advantage of this? Well, because there's so many cores, most of these loops can be completely unrolled and just have all the cores execute one piece of data on that loop. So instead of going for, let's see, they don't do it here. Oops. Knows that they're going to unroll this loop. So they get the ID for the loop and then they run the while loop that's inside of it. And the GPU will automatically chop it up into all the different processors and then it just sends it through the giant GPU that you have. Problems. Separation of the problem into independent parts. Some things, linear algebra. These are problems that map well. Random number generation, certain types of sorting, and then language processing. What doesn't do very well is any type of sequential problem, aka you have to do this computation before you can figure out what to do next. For example, compilation of the program is very serialized because you might have different pieces with different functions, so it's hard to speed that up. How do I program them? They support a lot of libraries. They've done Python, and many more languages have been set up nowadays. There's plenty of drivers, plenty of other libraries for different programs like MATLAB and Mathematica, but you can also just use CPI if you want to as well, or I'm sorry, C++. There's tools to help with debugging in other languages as well. Myths about the GPU. Some people think they're hard to program. It's not that they're hard to program, it's more that you have to learn another library. It does take some time to learn about it. It is hard in the fact that it can be difficult to understand what's happening, but most of the time you're just unrolling a single loop, which does increase performance. It can be similar, although they do say it's some of the myths. There is no assembler needed for this. Some people still think that it's not floating accurate. Nowadays with OpenCL it is. It used to be not. So hopefully they're trying to simplify OpenCL in order to let people leverage it. And the time is now. Okay, so a couple of things I didn't talk about were how's this architecture? Well, it's utilizing the processor on the GPU. So this is pretty much architecture all the way. Is it utilized a lot? Nowadays, yes. For any type of high performance computing, people in general will utilize the GPU as much as they can. And so it is also very popular. All right, now that's it for OpenCL. Next will come a security one.